to you is, how many people know that driving is the most deadly thing that you can do? Driving is the most deadly thing you can do. Every time you get in your car, you are having a chance where you're going to have some idiot rear end you or sideswipe you or do something. You can be perfectly fine and somebody else is going to be doing it to you. So you're never going to drive again, right? Because the possibility of you having an accident is pretty great. It's going to be the worst possible case of death that you have experience of. So you guys don't go to Duke and watch the game there. Or you don't drive to Franklin Street and jump over stupid freaking burning couches. Okay? We're going to talk about that in a little while too. Okay? There's always risks for everything, but the overwhelming thing that we have seen is that this vaccine, these viral-like particles, they contain no genetic material. So when these people who are anti-vaxxers say it's better for me just to get infected with the regular virus, the only thing we've got here is viral-like particles, the capsids of these viruses. The 4 main capsids, we're trying to make a more extended vaccine where we get 8 different strains that are the most oncogenic strains. Right now, some of the vaccines out there can reduce the ability to get cervical cancer by 70 to 80%. I had a friend of mine, one of my boyfriend's mothers, died from cervical cancer when she was 45. If we had this vaccine, she might still be around. Do I want you to vaccinate? I do. Have I told my nieces who are worried about this to get this? I have. Have they gotten it? They have. Have they gotten sick? They have not. The other thing that we need to do is we need to get this vaccine before you're sexually active. I just talked to you about the number of people who are becoming sexually active at the age of 12. So when do we need to get this vaccine to kids before they're sexually active? Anymore, I'm beginning to think 6. Okay, that's really low. Probably it's more like 10. But people are becoming more and more sexually active earlier and earlier all the time. So this vaccine needs to be given before you're sexually active, before you get the virus, before you get exposed to the virus. And this is the most common virus out there. So what else do we know about this? We know that wart removal can work to reduce amount of virus transmitted, but you're still going to transmit virus even without lesions. Pre and post reduction of the lesion can still transmit virus. Latex condoms reduce transmission, and it's the most cancer-causing strains. And when we talked about this, I wanted to remind you that when we talked about this, when this integrates into the DNA, this is when we see tumor formation, and this is what Henrietta Lacks died from. Okay? HPV infections, and if her family could have vaccinated her from having cervical cancer, do you think they would have done that? I'm just saying, I know I would. The other thing I wanted to show you, it's not just females who are at risk for cervical cancer. We know that we cause the majority of all, 16 and 18 alone are responsible for 70% of all cervical cancers. This is from the cancer.gov site, and the link is on this page. We have anal cancer, about 95% of all anal cancer. Oral pharyngeal cancers, because of oral sex. We get oral pharyngeal cancers because this is an organism that causes cancer. So I'm saying Michael Douglas with throat cancer probably had HPV in his oral cavity. And rare cancers, other cancers, penile cancers. So this is all due to this one kind of virus. And a vaccine prevents cancer in everybody who gets vaccinated. Okay? Okay. I'm going to say that about HPV. Now we're going to work on any questions that you have on Piazza today. Okay? So today we're going to start talking about the immune response. And when we talk about the immune response, I want to talk about how the immune response works. And when I first started teaching, we always thought of the wall between the innate immune response and the acquired immune response. The innate immune response did this, and the acquired immune response was much cooler, much hipper, and we wanted to study that. So the innate immune response didn't get studied much. Okay? And then all of a sudden, over time, we began to realize, hey, just like we began to understand that microbiota is important, hey, the innate immune response is important. Hey, the innate immune response is important. Holy mother of God, the innate immune response is important. Okay? And now instead of having two sides with this wall down the middle like we see here, we actually know that the innate immune response and the acquired immune response work like this. Okay? So now we have the innate immune response and we have the acquired immune response. We don't actually have a wall, but we do have a time differential. And I'm going to keep this up here because of the time differential. So when we talk about the innate immune system, the innate immune system are the things that work immediately to stop disease immediately, to help stop progression of viruses. How fast can viruses replicate? They can go plaid pretty quickly, higher, faster than exponential. Okay? So viruses, bacteria grow exponentially. So we need something that's going to be fighting off the organism while we are getting our super troopers going. Our super troopers are B cells and T cells. And notice the only thing in the acquired immune response are what? What is in the acquired immune response? B cells and what's the only thing in the acquired immune response? B cells and T cells. That is the acquired immune response. But you're going to need to know that we need the innate immune response to activate the acquired immune response. So only B cells and T cells are in the acquired immune response, but we're going to need the innate immune response to help guide the infection, to help guide the troops, because we're fighting a war now. It's microbial warfare. Okay? So we're going to need things like, we're going to need detectors. And the PRRs are our detectors, our pathogen recognition receptors. Okay? Those are the things that detect when we have flagellin around, when we have double-stranded RNA that indicates a virus is present, when there's flagellin around. When those things happen, our PRRs go off and alarms start being sent via something called cytokines. So we have cytokines being going off all the time. So we have cytokines, and cytokines also cause inflammation. We're going to talk about all of that today. We also have these things called granulocytes, and you can think of granulocytes as the primary troops of the innate immune response. They are the things that are ready, and their granules are full of toxic molecules. So they are prepared to be toxic immediately because their job is to simply throw their toxic molecules at things. So granulocytes have granules that allow them to be effector cells. So they're part of the innate immune response because they're granulocytes. Then we have something called complement. We're going to talk about innate lymphocytic cells, and an NK cell is an innate lymphocytic cell. And then we're going to talk about phagocytes and complement on Tuesday. Okay? So we're going to talk a little bit about how all these cells work and the way that these cells work and the way that this tissue works. But the most important thing that we don't really admire, you need to go home and admire your epithelial barriers. Okay? Love each other's epithelial barriers. Encourage them to be happy and healthy. Okay? So what do I mean by an epithelial barrier? An epithelial barrier is the first line of defense. It is the first thing that stops 99.999% of everything that gets in. Your mucosal epithelium, your stratified squamous epithelium. There are borders that these pathogens have to get through in order for them to infect you, right? So we have these first-line defense, and we're going to talk about the walls and antimicrobial substances. Then we're going to talk about our sensor systems, our PRRs and complement, and we're going to talk about how these things can activate these things. We're going to talk more about that, okay? Our first best thing is our wall, okay? So if you have a big enough wall, a thick enough wall, and you can protect your wall, you can prevent infections. But what happens when you have a big old hairy dragon that comes along and blows holes into your wall? How quickly do you notice your wall is down? What happens the last time you had a paper cut? How soon did you know you had a paper cut? Immediately, didn't we? So we have ways of detecting when our wall has been breached. And all the things we're talking about in the innate immune system allows us to know that our wall, our barriers have been breached. Or something is trying to get in. If something is trying to get in through the mucosal epithelium, what is the first thing you do in order to try and stop the thing from getting in? You sneeze, or you cough, or you blow it out onto somebody else, right? So we're going to talk about this. So all of these things help try to stop the organism from simply getting in. So we're going to talk about the epithelial barriers first. When we talk about this is the dragon that comes in and blows a hole in your wall. So if a microbe has the ability of blowing a hole in your wall, your border has been breached, okay? And you are screwed. And we're going to wait and find out soon what happens, okay? But with disease, I can tell you what happens. You get sick, okay? So what do we know about the epithelium? It comes in two flavors, two basic flavors. This is the body, and I always tell people this is Kim Kardashian because of this, okay? So, because I really hate Kim Kardashian, okay? Okay, so we have the stratified squamous epithelium on all the large curvy parts on the outside, okay? Then we have this, and again, the stratified squamous epithelium is really important at keeping things out because of the way it grows and the way it behaves, and we're going to talk about this in a minute. I want you to remember that the mucosal epithelium, and this is important, is one single layer thick. It's one layer thick. So we have to protect that mucosal epithelium a lot more. We have it inside of our tissues. We have it in our tube. And technically, we're a donut, right? So here we have stratified squamous epithelium, and here we have a mucosal lining that's one layer thick. We're going to talk about goblet cells. Goblet cells are these cells that produce the mucus that line the epithelial barriers, the mucosal epithelium, to trap microbes that have been breathed in and are trying to infect you. So here we have stratified squamous epithelium, and the thing I want you to know is that with stratified squamous epithelium and with these, there are stem cells that keep growing and keep reproducing to produce new skin all the time. So when we talk about this stratified squamous epithelium, these cuboidal cells at the bottom of this tissue are stem cells. And they grow, and as they grow, they divide this way, and as they divide, they push the new cells up, and the stem cells stay down here, and as they're pushed up, they start differentiating, and they start flattening, and the cell starts dying, and as it starts dying, it induces the production or the formation of something called keratin. So not only do we make this flat surface, but we're waterproofing our skin as we go up. So that keratin is now waterproofing our surfaces, and it's also interdigitated. We also have links between the cell surfaces so that when it's being pushed up, it's also a sheet of solid tissue. So has anyone ever tried to tear leather with your hands? If you've tried to tear leather with your hands, that is skin of cows. That is their epithelium. It's probably their dermis and their epithelium, but it's their epithelium. When you have been sunburnt, and you guys should never be sunburnt, what happens to the skin? Does it peel off in single cells, or does it pull off in a lovely stretch of dead skin because you've hurt your DNA so badly the cells had to die? That's what happened. So your skin is this protective, thick barrier against infectious organisms. We have this basal layer, this cuboidal epithelium that is our stem cells. It pushes up, it becomes keratinized and dead. So when we look at this on the surface, this is from chapter 21 and the skin. This is the skin, this is your stratified squamous epithelium. These are again, we're going to have the glands that produce the mucus, or we have, on the surface, we have sebum being produced from these glands. We're also going to have, notice our microbiota has niches that grow in on our skin. And when we wash, when we take showers, our normal microbiota still remains. They've evolved to stay on our skin. They are our protection from pathogens because they take up places where pathogens could get into, like MRSA, or something that could cause a potentially lethal infection. Our normal staph epidermidis, it's a nice, lovely protective organism that covers our skin. But I also want you to remember that the surface of your forearm is as different from the surface of your forehead as the desert is from the rainforest. The organisms that grow and live there have niches. It's a lot oily up here. It's a lot warmer up here. It's a lot different than these two niches. So we have microbiota that take up these niches. The other thing that I want you to know is that where we are most at risk, the wall gets thicker. So here is probably something from the palms of the hands or the soles of the feet where you're putting a lot of pressure, a lot of damage, possible opening that wall. We make our epidermis thicker where it's going to be more damaged. If you've ever had a cut here, this is very, very thin skin underneath your arm because it's almost always protected, right? So where we need it to be thicker, we make it thicker. We make the wall thicker. We make that stratified squamous epithelium thicker. And also, what do we know about this very, very top surface? What is it? It's dead. What do viruses need in order to replicate? Living cells. So can viruses replicate on our skin? So when we talk about human papillomavirus, human papillomavirus actually has to, call it micro fissures. There has to be a small break in the tissue, and it has to get down and infect these basal cells in order to start forming warts. Does that make sense? Because it can't grow on the surface of the skin to cause warts. It has to start causing warts here. And it causes those warts to start growing uncontrollably. Okay? So, when we talk about skin, we have epithelium. We make the wall thicker where we need it. We also are going to talk about mucosal epithelium. I am hoping that this works because this was a really great animation. And we just had a really great discussion in my department about how Pseudomonas, one of the worst pathogens for airways, can cause all sorts of problems. I'm going to just try to move this along so that you can see how this works. Okay, let's see. Is it going? So when we talk about our mucosal epithelium, we have cilia that line our respiratory tract, and we have, let me see if I can get this to work. Come on. Okay, so what I want you to see is how the mucosal epithelium works. So what we have is we have cilia, and the way the cilia work is on the surface of mucosal epithelium. It's important that they move together in a unified, we call it the mucociliary escalator. And it's important that they work together and that they all move together to allow this moisture. We use salt and fluid to line a barrier to create a place where the cilia can move in a fluid. So then we're going to add all of those cilia together, and that's what makes the mucociliary escalator work together. Okay, so it has to move like that, and then we're going to use those ion salt channels to pull in water and electrolytes so that those move in a fluid, and on top of the fluid we put mucus. And once we get mucus on top of that fluid, here's the mucus coming in, or here's the fluid. The mucus is on top of that fluid, and now whenever you breathe anything in, it gets trapped in that stickiness of the glorious mucus that you're producing. And as long as your mucus is thick and sticky, the organisms get trapped in there, and can they infect the cells underneath? They can't. So this is why we need mucus. You should love your snot. Make sure there's a lot of it. Make sure it's moist and thick and gooey. So what we find is that when we are in the winter months, we're indoors more often, and our mucus starts drying out because there's less humidity in the air, even though this is the South, and I do believe it tries to make us start breathing with gills because it's so humid down here so much of the time. However, we can see our mucus decrease from lack of humidity or when you don't drink enough water. If you're not as well hydrated and your mucus isn't very thick, a thinner, less tacky mucus means that these organisms can get in and start infecting these ciliated epithelial cells. And just like we talked about, even though this looks like it's multiple layers of ciliated epithelium, remember if you remember the term, does anybody remember the term for this? Pseudostratified. Because this is really one layer. It's just that in order to get all of these cells into one layer, you have to put the nucleus up here on one cell, the nucleus here on another cell, the nucleus here on another cell, in order to get 3 cells next to each other, right? So we have pseudostratified epithelium. This is our ciliated epithelium that's going to move that mucus along. And then we have the mucociliary escalator, and it's going to trap all of the organisms, and it's going to throw it into the acidity of the pit. So whenever I talk about the immune response, I always take it back to Game of Thrones. So if you're going to have, because I love Game of Thrones, okay? I am a geek. I like talking about Game of Thrones, give me dragons, give me dwarves, give me elves, I'm there, okay? So when we talk about this, we're going to talk about if we have a wall, think of the wall as your castle. Okay, so we have a castle, we're going to make tar, think of tar, we want tar to be hot and sticky and thick, just like we want our mucus to be thick and moist and gooey, so that organisms can't get to you very fast. And then on top of that, we're going to take this, we're going to have it a moving tar layer. We're going to throw it, anything that's trapped into our tar, into a pit of acid that's our stomach. So it's going to die in an acid pit. We win, okay? They can't stand after us, okay? So because of that, so all I can tell you is that on top of that, we're going to talk about how we have this mucociliary escalator, but if something does get in, and it does infect those cells, say a virus. We're going to talk a lot about respiratory viruses. So we're going to talk about the flu. When the flu gets in, it kills these ciliated epithelial cells. And if you kill the ciliated epithelial cells, what happens to the mucus? Can it move? It cannot. So the mucus builds up. We still have goblet cells, but there's nothing to move the mucus along. So we have the ability of still maybe making a little bit of mucus, but the ciliary escalator is gone. These organisms can get in, target these cells, and start killing these cells, and it takes weeks to grow these cells back. So when you have the flu, how long do you have a cough after you have the flu? A long time, because you're growing your ciliated epithelial cells back. People say, I still need antibiotics because I got this cough. No, you're growing your freaking ciliated epithelial cells. You don't need antibiotics. It's a flu, okay? So, to some degree. Okay, so when we talk about this, we're going to talk about the mucociliary escalator, and the flu can kill these cells, and when you have loss of cells, you've lost the ability to move the mucus. And so the only thing, since the cilia can't do it anymore, that's when you start coughing and sneezing, because the only innate response you have left is to cough and sneeze because your cilia are gone. So we see more coughing and more sneezing because the only way that we can move the cilia out of our lungs is to try and force it out physically. Does that make sense? And when you're in an environment where there's a lot more pathogens, or your body reads, when you're in a smoky place, say a bar, I don't know if you guys have ever been into a bar, but it used to be that bars had smoke in them in the olden days. And then you would breathe the smoke in, and it would get trapped into your mucus, and you would cough a lot, and your eyes would water a lot, and it's all an innate immune response to try and get that stuff out. Okay? The same thing is true when you breathe in allergens, or when you breathe in pathogens, your body responds by sneezing or coughing. Okay? These are large droplet nuclei. These up here, or these are large droplet, these are droplet nuclei up here that can hang in the air for hours. Okay? Question, one question.
I think you talked with live recording.
Thank you. Thank you. I don't know how long that was for. So, we have this mucociliary escalator. We have our first line defenses. We have the skin, we have the mucus. Okay? So, what else do we know about? We know that we have the microbiome. We know how important the microbiome is.